Hello everyone, welcome to Agent Mateo's class. Our topic for today is all about permutation. This is the first part of the Grade 10 Mathematics Quarter 3, Week number 1 and number 2. And this is Mr. Reyes, guiding you for our lesson for today. And our learning objectives are, we are going to use fundamental counting principle to determine the number of possible outcomes in a given situation. We are going to illustrate permutation of n objects and then derive the formula of linear permutation of n objects taken r at a time. We are also finding the linear permutation of n objects taken r at a time, and we are going to solve problems involving permutation. We will start with this warm-up activity. The outfits. A man has 2 pairs of pants. These are the green and the black, and 3 t-shirts which are brown, yellow, and blue. How many different outfits can he put together? Let us use diagram to figure this out. This is the man with his 2 pairs of pants. And each pair of pants can be matched with 3 different t-shirts. Match with this green pants. And we can also match this pair of black pants to the shirts. And from this diagram, the encircled portion here are the different outfits. To list them all, we have the first outfit is green pants and brown shirt. Second outfit, green pants and yellow shirt. Another outfit, green pants and blue shirt. Another outfit, black pants and brown shirt, black pants and yellow shirt, and black pants and blue shirt. So therefore, the man can put together 6 different outfits. Now let us have this problem. June has 5 t-shirts, 6 pairs of pants, and 3 pairs of shoes. How many ways can he dress himself up for the day? To answer, we just have to simply get those number of ways in each event or set of objects. So by fundamental counting principle, you will have this way. We have to consider the fundamental counting principle by multiplying 5, 6, and 3 from the set of objects a while ago, and that is equal to 90 ways. So therefore, if you will dress different outfit each day, you can have almost 3 months if you want to, just to use that 90 ways. That's how logical and realistic. So let us have another problem. A men's department store sells 3 different jackets, 6 different shirts, 8 different ties, and 4 different pairs of pants. How many different suits consisting of jacket, shirt, tie, and pants are possible? And once again, we will be applying the fundamental counting principle here. We just have to multiply 3 times 6 times 8 times 4, because our first set or first event has 3 different suit, and then for the second event there are 6, for the third event there are 8, and for the last one there are 4 given elements or different pairs of pants. So with that, the product would be 576, and these are the different suits that can be made out of this given set of from the department store. What if our situation now is we are referring to an argument which is the proper arrangement? It is important not only in getting the number of ways, but also we are considering the proper arrangement, because different order or arrangement means they are different in result. So therefore, I want to direct you with this so-called permutation, because permutation is an arrangement of objects where order is very important. The very first permutation that we know is the linear permutation. Later on, we are going to derive the formula in getting the permutation of ordinary objects taken a certain element at a time. So from this linear permutation, we are getting the arrangement in a certain row or in a certain line. So for us to derive the linear permutation, let us try to consider the following examples. How many ways can we arrange the following letters? We have A, number 2, A and B, number 3, A, B, C, and number 4, A, B, C, D. We will be applying the fundamental counting principle again. Through the use of the columns here, for the first column are the given set or the content of each set from items number 1 up to 4. For the second column, we'll be applying the fundamental counting principle, which applies the multiplication rule, wherein for you to arrange number 1, you will only have one way. For the second one, arranging A and B, we have 2 times 1, that is equal to 2. To list all of those arrangements for number 2, those are AB and then BA. For the number 3, we have for the first attempt, we have 3. For the second attempt, we only have 2 choices. For the third attempt, we have 1 left attempt or 1 remaining choice. So 3 times 2 times 1 is equal to 6. For the fourth one, we have 4 given elements from this given set. So there are 24 possible ways for you to arrange the letters A, B, C, and D. Notice that this result way or ways in getting or arranging the following letters can be noted in the so-called factorial notation. We have 1 can be written as 1 factorial, this 2 could be written as 2 factorial, the 6 could be written as 3 factorial, 24 is also resulted from 4 factorial. So that the numbers 1, 2, and 3, and 4 are those number of elements also from our first column. So n factorial is actually the way in getting the product of all positive integers from n, or the given element, or the number of elements down to the number 1. So again, let us try to consider the one of the problems a while ago. How many ways can we arrange the letters A, B, C, D? Since there are 4 elements in a certain row, we will now arrange that, and we could get the number of ways to arrange that by getting the 4 factorial, or 4 times 3 times 2 times 1 is equal to 24. For us to validate the number of ways, which is 24, we could simplify it or by listing all the possible arrangement. We have the following arrangement, okay, up to the very last, which is the DCBA. If you are going to count all of those, you will arrive at exactly 24 ways. But it is not advisable the listing. Just simply apply the fundamental counting principle or the formula behind the linear permutation. So let us try to consider this problem, because this will be the reason for you to simplify, or for us to derive the formula behind ordinary permutation. A while ago, we are getting all the objects taken all at a time. But at this point, we will be taking selected letters only, or selected objects only from the total objects. So how can we arrange the letters A, B, C, D, E if we will only selecting 3 letters at a time? Again, from fundamental counting principle, for the first attempt, our selection will be 1, 2, 3, 4, 5 choices. For our second option, since we already have one option or one selection from the previous one, so therefore we only have 4 attempts. And for the third one, we only have 3 attempts because we already selected 2 from the given letters presented for our problem. So multiplying that, you will have 60 ways. Again, to get the permutation of n objects taken r at a time, we'll be using the fundamental counting principle. We started at 5 times 4 times 3, but at this point, we will be multiplying both numerator and denominator by 2 times 1 and then 2 times 1, because we will arrive at 5 factorial over 2 factorial, which is noted to be factorial notation as long as you ended with the last part of times 1 and times 1. Notice that 5 is given from the problem, which is the number of letters given from the problem. How about this 2 factorial? That is not actually visible from the problem, so therefore we need to simplify that by interchanging it to 5 minus 3, or 5 is given from the problem, which are the 5 objects, and 3, wherein those are the 3 selected letters. So we could rewrite the 2 factorial into 5 minus 3 factorial. So we could simplify that in getting the permutation of 5 objects taken 3 at a time could be simplified by 5 factorial over quantity 5 minus 3 factorial, where in general, the permutation of n objects taken r at a time will be denoted by this symbol, where order is very important, or that is equivalent to n factorial all over quantity n minus 3 factorial. Will you try to solve this given problem? Sheila has 7 candles, each of different color. How many ways can she arrange the candle? And the candelabra that holds 3 candles. And once again, the given for the value of n is 7 and the value of r is 3. So we are going to get the permutation of 7 objects or 7 candles taken 3 candles at a time. So we will use the formula, substitute everything, and you will arrive at exactly 210 ways for you to arrange the 7 candles taken 3 at a time. How about these problems? I want you to pause this video and check your answer later on. And the answers are, for the number 1, that is 5 factorial or 120 ways. For the second one, we are going to take from 100 names, we will only getting 3 at a time because we only have the first, second, and third to be drawn from a certain box. So that is permutation of 100 objects taken 3 at a time, or that is 970,200. For the third one, how many different ways can 6 bicycles be parked if there are 4 available parking spaces? Again, from 6 bicycles, we only have to allot 4 of them from the available parking spaces. So 6 bicycles taken 4 at a time is equal to 360 ways. And for our last problem, we will apply the fundamental counting principle here. It was stated that the problem has repetition is allowed. So meaning to say, in every space here, you will still repeat those digits to be used. For the first attempt, you can use 6. For the second attempt, you can use another 6 of the digits here because repetition is allowed, and another 6 and another 6. But for the last part, it's a different scenario now. As you notice, when you say even numbers, we only have to select the last digit as even number. So therefore, the even numbers from the digits are 6 and 8. So therefore, you will be using 2 and the last part of our 5-digit number. Multiplying everything, you will arrive at 2,592 ways. So that ends our lesson for today. For our next meeting, we will be discussing another type of permutation, which are distinguishable permutation and the circular permutation. So with that, let me end my discussion with this quotation. We have, if you really want to do something, you will find a way. If you don't want, you will find an excuse. And once again, there are many ways out there to cope up with your studies. With that, thank you for listening and have a good day.